All right, so we go straight away into the machines. So I will start sharing one machine per time. So during this workshop, we are going to have a little dive in also into the CAD model of the machines. We're going to discuss technical details. If you have any questions, please, you can type it in the chat, or you can interrupt the conference and ask it directly the question. After we will see the machines on the screen, we will see the machines for real, that they are all working at this time that they are talking. And I'm going to show you the machines, the mechanical parts, even from the real camera, from the real perspective. And then you can ask also questions, you can see the results, and anything that you think. All right, we will first start with a 3D printer, which is called MidFDM. And I'm going to show you basically some pictures that I have online, and then we go straight away to the CAD model. So I published all my work into this website that now I'm sharing to you guys. And here you can find many pictures and many updates about what I'm doing. And so we will talk first about the 3D printer. So the 3D printer is called MidFDM because I was building a big FDM before, so this was a sort of a middle size. And the aim was to build a machine that has a quarter cubic meter printing area. So this would mean like 500 by 500 by 500 millimeters. So this was designed for this Fab Lab in Ghana. And then bill of material was intended to be around 1,000 euros. So we, $1,000, sorry. We ended up on being a little bit more than that. I think it was something around 1.5K. But with the optimization of the design, this can be further lowered down. You know, every machine for me, it should, every new development, it should like answer a research question in terms of making. So because if I just copy another 3D printer or just make one, okay, it's fine, it's nice. But nowadays we have lots of 3D printers that are replicable and that are open source and so on. So the question that I wanted to answer in this printer was, can I make a cantilever system to 3D print something? So you know the cantilever system is a system that basically hangs everything on a single arm. And the motion system connects all the three axes together. So you have basically X, Y, and Z all together connected in a single arm. So the challenge of this printer was this system, because this system would cause many vibration, probably. It needs to be quite well designed to be stiff enough to print something reliably. And the reason why I was doing that, it comes from the previous development of Big FDM. So Big FDM was presented in the previous workshop. It's this gigantic printer that I made before in the past. And one of the issues that I realized in this printer is the complexity, for example, of the Z-axis. So this is the design of the Z-axis. And the Z-axis moves the bed up and down, as you can see here. And to operate this motion, I would need to have 4 lead screws, 4 linear shafts, 4 linear bearings, 4 platforms on the side, plus a very complex system on the bottom with a closed loop bed. So I could also have, of course, 4 motors, but then this would mean 4 drivers or more powerful drivers to drive the motors. The motors should be synchronized as well. So there are even more complex systems than that. By the way, this one was already quite complex because I needed to make sure that all the 4 points were almost the same height in order to not make the motion being blocked by the fact that things were not flat, and the trapezoidal nuts that are here, the brass nuts that are here, will create lots of friction if things are not flat, and then this will simply stop. I don't know if you had this problem usually in the laser cutters, that the very old, maybe you never went too far down, and then it blocks after a while. So the aim of this was to create a simpler system, which involved much less components into the design. For example, I would use only a single rail for the Z-axis to go up and down, and a single lead screw instead of 4, for example, and so on. So here there are some pictures of the machine that is being tested for one of the first times. And here there are some first results, so you can already see a little bit more about the real shape of the machine. So the bed is fixed completely, and then the head will be moved by this sort of cantilever system over here. So the machine is practically finished. But in reality, we still have some little issues that we are fixing along the way. And of course, one of the issues that is more difficult to fix is the wobbling or the motion that these arms create. So my question was answered, which was, okay, can I design a cantilever system 3D printer? Yes, I can, and it works. It's proving that it's working. But then it needs to have some further refinements and especially some kind of maybe control on the motion system in order to avoid the vibrations of the axis. So it works. It's quite cheap in comparison to other systems. It's very easy to assemble. You know, it leaves you also a lot of space around the printer and so on, but it's creating these problems. So now we can go to the CAD directly, and we're going to see a little bit more about the CAD. Okay, so guys, don't be shy if you have questions about the printer itself.
Daniele,
yeah.
I have a quick question about the resonance that you mentioned. Have you tried anything in software to compensate? Like, I know Clipper has an input shaper where they mount an accelerator on top and then they can compensate for motion in software. Have you tried that?
Yeah, so for now, the only thing that we tried was to, because also this printer was built in the last 3 months, we tried to play with the jerk and the acceleration settings, both in Marlin and in the slicing software. And then there is a student that actually made a thesis about checking some of these aspects, still from Professor McGill. But the further approaches will include what you just said, so measuring the acceleration, have some kind of compensation in software. We have to see if this can be done, for example, directly in Marlin, or modifying the Marlin, or it can be something completely separate from the Marlin, where it's directly the controller that maybe it has a closed loop control to the motors, and then with this it can check or it can adjust according to the vibrations. So we have to see if it's something transparent to the Marlin or not.
Thank you.
All right, so let's have a look to the CAD of the machine. So we will remove everything from here, and we will start with the bed. So the bed, guys, is a simple plate, simple 6mm aluminum plate that has been milled by us, and it is attached in many points, and each of these points has a spring. So here there will be like a screw with a spring, and then this would allow you to regulate the flatness of the bed or the orientation of the bed. And this design has been made on purpose because if the bed warms up and it expands, then it has space to expand without deforming the frame or damaging anything. So if we start with the y-axis, so the y-axis is a simple linear rail, and it uses an MR24 motor that I always find a good compromise in terms of torque versus current that it takes, because it has 4 Nm of torque. And then the system uses a belt and then some custom-made pieces to connect the motor to the frame. And then this system, it's a very strong one because it has 2 linear guides from Highwind. Those are the HG15 linear guides and 4 carriages, because this is the point where the most of the force will try to distort the movement. So then we have our Z-axis, which basically stays on top of it. And the Z-axis basically employs an MR23 motors because the Z-axis never moves too fast. And it uses a custom-made aluminum piece over here, which joins the old part. So it joins the axis, the Z-axis, together with the linear guides of the Y-axis. It uses also this bracket on this other side, and the profile on the bottom is tapped. And the screws are passing through from the bottom here, and then this would attach also the profile from this other side. So then the motor has a coupler over here. Here there is a lead screw, and then there is a brass nut that moves the whole system up and down, and then 2 footer carriages and 1 linear guide over here. So the profiles have been used as a base for the linear guides. It's quite highly recommended because these components are highly modular, ready-made in the market, very cheap, I have to say, here in Germany. So we are in the range of some euros per meters, depends on the size of the profile. And then they are quite straight and flat, and they have these rails where you can put T-nuts inside, and then you can easily attach and center the aluminum profile. So if we continue with the x-axis basically mounts on the z-axis, and it uses this CNC milled piece of aluminum that has some tapped holes inside here. And then this kind of triangular shaped CNC mill plate. This is, I think, 12 millimeter aluminum here. And then this employs another aluminum profile, and then another NEMA 23 motor, and a belt, and then a linear guide again of the same kind. And then here there will be the head of the machine printing. Yeah. So there the machine, it's very simple. It has a filament hole here where the filament is going to be directed to the extruder. But for the extruder, we have a E3D Titan extruder, and then here we have a holder for the sensors. So for the bed leveling sensors, so we use inductive probe sensors to level the bed, and then also for the z-axis for the Z-min and stop sensor, and then we use normal mechanical micro switches for the rest of the machine. So the overall frame of the machine has been built on this structure, and it's made by very cheap 2020 aluminum profiles, just to make a housing for the machine. So the machine is fully enclosed, and the housing is realized by using aluminum composite panels that are very easy to cut, and also laser cutting and acrylic. So I have here with me a piece of aluminum composite panel. If you want to see it, it's basically a thin plate. This is 3 millimeter. It has aluminum on the top and aluminum on the bottom. The thickness of the aluminum here is in the range of 0.2 millimeters. And then here you have a material in between, which is basically plastic. So usually is PVC or other kind of plastic. So this material, guys, gives you some properties of the aluminum because it's rather strong. It's very strong, for example, in terms of bending, but it's very easy to CNC mill it and cut it with a simple tool without risking that the aluminum will stick to the tool, and it's very easy to handle. So, and it has some also isolating properties, and it's made also to stay on the outside. So the material is quite strong. I use it for many housing for my machines now, so I highly recommend you to use this material. So we go back to the CAD. So this is the final shape of the machine.
Before you move on, that material, at the moment you've got it on it's got a white surface on it. Does it also come with just an aluminized surface, or is it always that white color?
So it comes in lots of flavors. So you could have the natural color of the aluminum if you want, anodized aluminum, anodized with color, with special coating resisting to specific weather, another color. Yeah, it exists. It's a standard material, and it exists a lot of forms. So here in Germany or in Europe, you can find 3 millimeter within these features. So the side will be colored as you want for 3 millimeter. In Europe, it's also easy to find 6 millimeter, but it's only white. If you go to US or China, you're going to find 6 and 8 and 10 millimeter, also with many different colors and flavors. All right, so we have been doing this housing here, and then later on the machine, there was on top here had a sort of a spool holder, and then here there is a hole where the filaments will go inside, and then a couple of doors that are closable by magnets, and this was the old printer. So maybe worth to show is that in the back of the machine, we have separated our electronics. So in this box here, we have a door, and here we have placed all the electronics. I'm sorry that the 3D model is not so polished, but this machine has been built like in a rush in the last months, and we haven't still put the screws on it. So here there's going to be the old electronics, and this is completely integrated into the machine, and it's a separate, let's say, place from the motion of the axis. So the axis itself can move up to the back of the machine. There is still some space here to move, but here there will be this separate space for the machine, for the electronics. So here there are the holes for the plugs, USB plug and power plug. All right, do you have some questions before I go to show you the machine in action with some pictures and videos?
Daniel, one question.
Yeah.
Regarding the resonance of the cantilever arm. Have you thought about or tried out to extend the arm backwards and put a counterweight on it to reduce the resonance?
You mean in this position here at the end of the axis?
Or the other end?
Here.
Yep.
No, we haven't tried that yet, but we have made this axis, this profile is rather heavy. We have made this part as the heaviest of the machine. But yeah, we should try still to play with some weight.
Because what I understand of the crane technology is like they have, you see the big cranes on the building areas, they have like on the back part these counterweights to reduce, you know, either the energy and also the resonance. Yeah. So I was thinking maybe this would help instead of trying an electronic solution.
Yeah, that could also be. That could be also taught for the next development of the machine. So this version right now is going to Ghana. We have fixed it, it works, but then Professor McGill is going to build the next one. And for the next one, all these considerations, software and hardware, will be taken into account. So what we have also tried just quickly was to reduce the weight of this axis, to make it lighter, way lighter. And guys, this resulted in much worse results. So the heavier was this axis here, and we thought about this because this profile is a 30 by 60. It's able to give more smoothed oscillations than the small one that is more nervous and gives like more shakiness or something like that. Yeah. So the answer to the research question is yes, you can do it. It works, but it needs some improvements to be proved. And till now, you know, we have still to evaluate. So the simplicity in assembly and production is for sure worth it in comparison to the complex printer, but the cost of it is still rather high because one of the goals was also to save the cost. So this approach, you know, it's something that needs to be still validated. All right, I'm going to show you guys some.
Question. Question. I'm Haru from Japan. Does the table, does the table have the heating system?
Yes, the table has 750. No, I think it's 1.5 kilowatt heaters, and there are four heaters here. They're not drawn now in this schema, but there are silicon heaters, AC heaters. And so AC heaters, guys, I'm going to show you in the machine maybe. They are, for me, the best heaters because they will heat very fast. They are cheap, they're very powerful, but they have a huge drawback, which is they work at 250 volts. So you need to be careful because they are going to be connected to your aluminum part, and the aluminum part is connected to anything. You know, so and the machine is also grounded. So if you have problems, it's you need to do well the electrical insulation and so on. You have other questions?
Okay, thank you.
Yeah, sorry, I skipped this part. All right, we're going to be into the website, so we will see quickly some videos. So this is the finished machine over here, and so one thing that we implemented was to use this inductive probe. Guys, I was not used to work with these inductive probes, but now that I use them, I recommend you to use them everywhere in your machines. They work contactless. So this means, guys, that they're not going to touch anything. And then, guys, what's going to happen is also that they will be very precise. So we measure the precision of these things, and they're in the range of 0.05 millimeter precision. And they're quite cheap. Here in Europe, you can find them for something about 4 euros each. The only problem you're going to face is that these are going to consume some milliamps. So they're not easy to connect to the microcontroller as you would do for the mechanical end stops, and they work then with another voltage. Usually is from 6 to 24, some from 10 to 24, something like that. So you need to make something to adapt the sensing, and we have made a self-made board to do that. But since you do these self-made boards, guys, I highly recommend you this. So we have implemented, of course, the automatic bed leveling. And this is a video about it. So the machine is basically probing the old bed. And because if you have a bed of this size, guys, you're never going to find yourself the leveling. So the leveling is still something that you can do by hand, by screwing or unscrewing these screws. So there are springs under them, but then you need this system. And something to mention is also the controller, guys, which is, this one is our controller. This is MKS S-base 32-bit LPC microcontroller. And so online you can find a repository, but I'm sorry to tell you that it's not open source. But the reason why I use this is not because this is not open source, it's because there is the beautiful LPC, I think it's 1768 microcontroller, 32-bit microcontroller. And this LPC, guys, is compatible with Marlin, Gerbil. And with this means that you can use it for all the machines that we are making. So we are shifting towards a unified controller. And in the future, what we will do is we will, of course, design our own board around this microcontroller and make use of this board in a modular way for all our machines. So it has very high performance. It can predict many movements in the future for all the firmwares. And especially, it can do picture engraving into laser cutting, which is not so easy to be done quickly. Okay, Christian, you have a question, I think.
Yes, I saw your the sensor that you used for automatic bed leveling. As far as I remember, there were two types, a capacitive and inductor driven sensor, and one is actually more friendly with the steel sheet. Which one did you use?
I use the inductive sensor here.
Okay.
That is not so friendly, but it gives, I have to tell you guys, the best results. So the distance depends on the material that you have underneath it, which means, for example, if you use steel, the induction is going to be sensed before than aluminum because it's much more conductive, for example, or copper, for example, something like that. So you can adjust this distance according to the material that you have underneath it. But this is really, really, it's something that saved the machine. Otherwise, it wouldn't be able to print it. So I will do this with Marlin, with the standard Marlin. So some printing examples here. Here's this was printed at the end, guys, at the furthest point of the axis of the machine. So the shakiest point, you see where it's printing is printing over there, and it's still, let's say, quite acceptable as a result. And here there is another print. This is a very fast print that we tested just to see if the shaking was happening. But as you can see here, guys, the shaking even at this speed, it's almost something that you cannot notice. Yeah, and you can see the machine is going back and forth. Yeah. All right, so I think we are over with this machine. We go to the next one, and then I'm going to show you the machine live. Do you have further question? All right. So the next machine that I'm going to show you guys is our beloved small laser cutter, which is something that you can also find on this website. And so let me go down for it. This was the first version that we have made last year. It was the first approach of making like a sort of affordable laser cutter, nothing crazy like Laser Duo, nothing impossible to replicate, like that giant machine that costs like more than 10,000 euros, and you need to cut 20 plates of aluminum to make it, but something that that it's more affordable, small, and it's easy also for us to make it. So this machine has a cutting area of 600 by 400 millimeters. The bill of material is around 1.5 thousand euros, 1,500 euros roundabout. And now we have shifted towards the new version, which improves many aspects of the first version. We have a better window. We have mostly only aluminum parts in the machine, and we have improved our bed system, and also we have a better calibration system, and so on. So also for this machine, we are going to go to the CAD, and then I hope this works. Yes. And this machine, it's here. So we can start removing a couple of stuff. We look at a little bit inside. So let's look the housing. All right, guys. So there is always inside my head a huge discussion about using or not these aluminum profiles. And I'm a slave of these aluminum profiles because here in Germany they are so cheap, and the companies, they will cut the profile to you to the right length that you want, even though your length is 55.5 millimeters. You know, they cut it very high precision, and they come out of the factory rather straight. So if you also use the surfaces of the profiles and some aluminum brackets to square the profile, your frame is going to be square. And on top of that, you can screw on any point of these profiles along the rail. So you just put T-nuts and they become surfaces available to screw anything on them, you know? So, and this is something very big that is running out in my head right now, because, you know, the right way of making a laser cutter is to laser cut and bend steel plates and then powder coat it. And then in 1 millimeter steel, you have the power to screw something onto it, to tap something onto it. But then who's going to be able to replicate this machine in Fab Labs with bended steel plate? You know, it's going to be very hard. So I'm still using profiles at this time. And later on, I will try other approaches. So, and this is basically the frame of the machine, which is composed basically by 30 aluminum profiles. And it's basically a box. These profiles on the top have been increased in size. So they are 30 by 60 aluminum profiles to give more stability to the motion. So the aluminum profiles here have been used at least for 3 objectives. One is to close the machine, to have a housing. Second is to attach almost everywhere anything that they need. And third, as a support for the linear motion of the machine itself. So let's have a look to the machine axis. So we have here, let's put inside first the inner housing. So, and so this is the inner housing of the machine. It's made with this, the same material that I was talking to you before, this aluminum composite. This name is also, the name of this material is also D-bond, commercially cloned, in Germany at least, or in Europe. And you see this material has been used just to create some reference planes where I would place the electronics and the laser tube, and to enclose and to separate the laser cutting chamber, so where I'm going to cut, from the rest of the electronics and the mechanics. So the y-axis is based on a single motor. This is a typical design that you will find in laser cutters. So you will find a single motor somewhere in the back of the machine, and then to the motor there are 2 shafts, and these 2 shafts, they drive 2 pulleys on the side, which they are attached by aluminum millet parts to the frame itself. So these parts over here, and here there is a bearing. And then in the front, you will find a free running pulley and an aluminum parts that attach this pulley here. So the aluminum, the laser cutter gantry should move rather fast, and so it should be as light as possible. Some designs, they use 2 motors on the y-axis to improve the speed, but in this case, a single NEMA 17 motor, dual shaft motor in this case, was enough to generate a motion up to 600 millimeter per second in this case. All right, so this is the y-axis, and the y-axis, guys, relies on the profiles directly. So the linear guides are the still high wind MGN 212, and these linear guides are directly attached to the aluminum profiles. So it's worth to mention that I also created some fabricable linear guides, or fabricable linear guides, that they work very well, but they're made out of POM plastic, so Berlin plastic. And in this case, this stopped me for using these linear guides in this machine because of fire issues. So because POM is plastic, can take fire, so as many parts in metal are here, it's better. And also, it's very hard to make them as precise as these rails. So this is the y-axis. The x-axis just appends on the y-axis, and it's composed basically by some holders that attach directly to the linear guides, and belt is basically attaching to the carriages of these holders over here. And then these basically move another 2020 aluminum profiles, which host a similar linear guide, and then the head is over here. So here is the machine head, and then that's basically it. So the y-axis carries the x-axis, and the x-axis is directly attached to the motor here. So the one thing that is worth to mention in comparison to standard laser cutter is that this saves a lot cost, because usually the laser cutter, they have an inner structure which it's standing somewhere here, which has the motor and the electronics and many other things on the side. So by putting the motor here directly inside, what I did is I avoided to have further inner boxes inside the machine. And everything, it's integrated basically for the motion of the x-axis inside the laser cutting chamber here. So I also enabled the laser tube. You can see the laser tube is on top of this aluminum composite panel, and it's using standard holders that are regulable in height and in the position in this direction as well. And then here there are a couple of mirrors that will bring the laser. Basically, actually, you can see the laser beam here to the x-axis. So this kind of design for the motion of a laser cutter has been proved not only by me, but also by the big producers like Chotec or Epilogue and so on. The only thing that they do is they use some kind of additional pulleys, so they don't attach the shaft of the motor to the shaft of the axis directly, but they use some reducers because they have to move longer lengths. And these reducers are basically held by strong bearings, so they can achieve fast motion and longer motion. But in this range, so 600 by 400, still to attach this direct to the motor is okay. And then the linear guides used are quite fast. So this kind of like one motor on the back and one motor for the X, it's implemented in almost all the laser cutters. So then the rest of the machine is rather easy. We have the electronics that is separated from the laser over here. And we have the high voltage here on the right and the low voltage here all on the left. And here we use still the same controller, but we also use something that I'm showing you now in the screen, which is a sort of utility PCB on top of the controller. So I will stop sharing my screen and you should see my camera better now. So there are a couple of quirks that we discover all the time for laser cutting, which are very important in case you make one. So first of all is that, of course, you know that the signal that is being output from the microcontroller is not going to be very strong. So you're not going to have many milliamps in that signal, first. And secondly, sometimes you don't get the right voltage to which you need to operate the device. For example, in our case, the laser power supply works at a signal of 5 volts. So it takes pulse width modulation, PWM, but it works at 5 volts. But our board, it outputs only 3.3 volts. So we need to make a logic converter. But not only that, we need to make sure that this logic converter sends the signals at a specific frequency. Because if the logic converter is rather slow in outputting the signal, then you're not going to encrypt anything and you have horrible results. So that's why we had it. So these are very simple, stupid PCB that I made. There is here a logic converter on board, this red one, which is a ready-made component that you just use a couple of transistors for doing that. And the clue to increase the frequency of the output is to put some pull-up resistors at the end. So this one has 10 kilo ohm pull-up resistors in the output. And we put to that in parallel 1 kilo ohm resistor just to lower the resistors in the pull-up resistor to have stronger current in the pull-up of the output. And then this will raise up the level very quickly. So the discussion is a little bit complex. Basically, what's happening is that the signal, you know, when there is no signal, this outputs logic level high. It's always pulled high. If the microcontroller sends a low signal, then it's going down low, but then how fast it can raise up. And this how fast it can raise up is given by the pull-up resistors in the output of the logic converter. So we discovered that the standard logic converter was not fast enough. And our engraving of pictures, which they required several signals per second, were not happening. So slow cutting was fine, the others were not. So there is also an anti-tiny here on board that we use to drive a sort of safety switch for the machine, which is a relay. So there is a relay which cuts off the communication to the laser power supply, and it's driven by this microcontroller here. All right, we can go back to the CAD. So the all electronics is here, the relay is here. We use external drivers because we want to have all the power of this small NEMA 17 motor. So we use Toshiba TB6600 motor drivers here. And then we just have a 24-volt power supply. And here we have a laser power supply. So in the machine, guys, so once you close the machine in the housing, here. So what you will realize is that there is an emergency button here that now is with the key, so you can cut off everything. But there are two sensors for the windows. So if the window opens, the laser is going to stop being output, but the motion will still happen. So there is a mechanical switch here. And then there is also a magnetic switch over here. So we have double switch for the window. So in case you open the laser cutter, this will shoot off. The rest is quite similar. So you have basically a CNC milled aluminum composite housing. And then you have some 3D printed parts and some other things. Maybe it's worth also to show the exhaust system that we have implemented. So we remove this. So the exhaust system, guys, it's basically just a pipe that bridges the electronics, but no smoke is going to be in the electronics, and that catches the fire directly from the laser cutting chamber. And then here there is going to be attached a filter that brings the air out. So another thing worth to mention about the electronics is that this is a nice design in case of let's say making the machine more safe, or in case you want to certify the machine, because it separates the high voltage from the low voltage. That is something very important that you need to do. But still, we discover later that there are some quirks and some problems in the communication between the microcontroller and the laser power supply, because the laser power supply, guys, outputs 18 kilovolts and milliamps to drive this 40-watt laser tube. So these high voltage, guys, will create an immense noise inside your machine, and these are aluminum composite panels that can be also like capacitors somehow. And what happens is that if you don't use shielded wires and you don't put the wires far away from each other, you make the wiring correct, then your machine is never going to fire. Every time that you try to fire the laser, the controller will simply reset. There is too much sync out of the communication, and then the microcontroller, boom, it resets. Or you have jobs launch in 1 hour, and then they stop and you lost the entire job. So this is something critical. So another point that is critical that we address in the new version is that the laser tube is water cooled, and the pipes are going to be on this plate here, And if this system fails and the water fails, it will go straight into the electronics, making some nice, problems and short circuit and so on. So all these issues have been taken into consideration for the next version that is coming soon. All right, so the machine, guys, doesn't have any Z-axis, but it only uses this kind of aluminum modular bed. Maybe I will remove the rest so we can quickly check on it. So this is a bed that has been built with aluminum profile brackets, and these kind of L-shaped aluminum brackets that you can buy here in Germany on the market, those are 0.8 millimeter aluminum brackets that have been smoothed on the top. And these guys have a distance between each other of 20 millimeters, roundabout. And then what happens, guys, is that this is very different from the honeycomb of a traditional laser cutter. The honeycomb is so dense, so fine, that you're going to have lots of firebacks to the piece. With this one, you have firebacks that are more coarse than the other one. And also the distance that is in here, so from here to the top, makes the laser highly unfocused in a way that this will never reflect back the laser, either to the machine or to the piece itself. So this bed is something that we are, because I know I can buy a honeycomb ready-made of this size. It would save me a lot of time, because I'm cutting this by hand, smoothing them by hand, and gluing them by hand to the bed myself. It's a lot of work to produce this bed, and it costs also more than €100 only this bed. But then, guys, customers are loving it, and we are super happy with it. So we're going to keep it. What we're going to do probably is to make some holes here in this profile, so some kind of design that the exhaust can be taken directly from the side of the bed. All right, and this was basically it for Fabulaser. I'm going to show you a couple of videos of the machine, unless you have some further questions about the machine.
Question.
Yes, please. Hello.
This system is using the CO2 laser with the mirror system and the water cooling. So what about using the solid state laser module? I think it is the way to make it a more simple system.
You're absolutely correct, because if I would have to use a laser diode, I would only have the diode here with some electronics, without water, without 18 kilovolts, but only 24 volts or 12 volts, and it will be much simpler system. The machine will be much smaller. But the problem is that although I think that these diodes are the future, and in some time they will become powerful enough to cut as we cut with the CO2, still the CO2, it's unbeaten for the performance that it does. So this machine, guys, I will show you in real time, it will cut 10 millimeter acrylic with this CO2 laser. And it's something that you will never now be able to do with the diode laser. Yeah. Haru. More questions, guys, about the machine? Haru, do you have other questions? Finish. Okay.
Okay, thank you.
All right. So the design has lots of problems also, because I was telling William yesterday, it has too many parts. And if you are somebody like us that will calibrate the machine easily, you know, it's easy to make this square and straight and so on, but it's horror to assemble it. It takes too much time. And so in the future, I'm going to make a huge reduction of the part list in a way that also for us to order and label them, it will be much faster. So the next design will have the x-axis as a one piece. And now it's a linear guide here, profile here, this holder here on the right, one other holder on the left, lots of screws over here, you know, and this is a huge problem we have right now. Also, there is too much freedom in calibrating the mirrors. The mirrors can move in X and Y direction. This can move up and down. In the future, we will make like press fit slots where things will fit in, you know, and they are pre-calibrated or almost pre-calibrated. So in the future, we will also use a laser tube with coaxial laser pointer inside, and this laser pointer inside will basically allow us to make the calibration without using the real laser. So right now, to make the calibration, we fire the laser, and then we see a spot on a tape that we put here in the space of the mirror. Now we have a laser tube with coaxial red dot that is the same position of the laser. So you can use that to see the position of the axis, of course, in the machine, like as you would do in an epilogue or Trotec. And you will also use it for calibrate the machine, which makes it much more safe. So you will fire the laser only when the machine is closed. Okay, just to conclude, we have further safety features. We have a water flow sensor that it will not shoot the laser if the water is not flowing, so it's automatically controlled. We have this relay that will shoot off the laser in case something is happened. So this, for example, if you trigger the hand stops, the laser will be shut off. If the microcontroller is kaput, is broken, this will detect it because maybe the voltage is crazy and so on, pum. And this will stop the laser immediately from firing. All right, so I'm going to show you the website where we have some pictures and some videos about the machine. So I'm forced to change the sharing. So here is the kit of the machine. So how it comes at this time. It's basically a kit, it's all labeled, and you can buy the kit from us. And the kit is all included. You don't need to solder anything to assemble the machine. All the cables are also like ready crimped. You just need to screw them into the right spot. And we also, so here was the first prototype that was copied from the first one. We are running workshops building the machine. So people have a very nice manual that is just finished. And we received all the parts like labeled, as you can see here. And this is a screenshot of the manual that we are making that we discussed in the last workshop. It took us like 6 months to make this manual with 2 employees doing it, guys. So it's going to be a very good one. And yeah, here you can see some videos of the machine. I'm going to show you some real-time also videos. So this is cutting MDF 3 millimeters at this time. Right, and here is engraving a picture. So guys, I was able to make this picture only after implementing the changes to the output of the logic converter, guys. Otherwise, I would never be able to make this picture here. Yeah. So the machine is very compact and it's weighing less than 60 kilos. It's easy to transport. You can put just on a bench. All right, then we finish this machine and we go to the next machine. More questions about these laser cutters?
You told that there's a filtering system in progress, like air filter.
Yeah, so the air filter, it's something that it's like, you know, sorry, like pain in the ass, sorry, because it's very, very expensive now. And it's something that is very closed. So this means basically that you are forced to buy so this is a filter that we are making, and these are the cartridges of the filter. And the filter that we use now uses proprietary cartridges. So you're forced to buy these cartridges from that supplier, and that supplier is going to make you pay lots of money for that specific shape. So we want to go out of this, you know, crazy business, and we are trying to build it. So this is a filter that we are building now. There are a couple of clues about it. This is the overall structure. Maybe I reduce the size of it. So one clue, of course, is to let the people replicate it and it becoming cheaper, of course, of other machines. Another clue is to decouple the fan from the filter itself. So many filters, they have a fan integrated inside. But this fan, you have to take care, is a fan that is not usable elsewhere. So it's inside the filter, and you know you cannot detach it and make a use of it to exhaust something else. So it's not modular. It's a closed black box. So, and with this filter, we decouple the fan from the filter itself. So the filter itself, it's only the filter. It has only the filter cartridges, and that's all. And then we provide to the user also a separate fan, which is not in these pictures. Why? Because the user can use the fan for something else later on, can recycle it, but also it can use the fan to exhaust when it cuts, for example, plywood. So for example, here we are obliged to use a filter when you cut plastics. But when you cut plywood or something simple, you can often exhaust it directly onto the outside. So you don't need a filter. And doing this, you will save also the life of your filter. So we would like to provide a filter with separate fan. And the user can attach the fan only when it wants to cut wood. And it can touch the whole filtering system when it wants to cut plastic. So this will save a lot the filtering life. So this filter is very simple. It's a box made of aluminum profile, some aluminum composite on the side of the filter, and it involves a G3 filtering mat on the top that is not shown on this picture. Then it involves a F9 pre-filter, then a H13 HEPA filter, and then a laser cut box full of active carbon that will take the smoke. So guys, we have been measuring this filter with professional equipment, and the filtering of the gases is better than our commercial filter. But the filter of the dust is not. It's 2 times worse than the commercial filter. So we are still not there yet. And we think that the problem is the isolation of this, because this is basically pushed on top of each other with pressure, and there is a sort of rubber ring around it to make it tight, but it is not tight, and some dust is coming out. So this is not ready yet. And if it's ready, it will cost half of the price of the normal filter. And users can buy this filter. Those are standard size. They can buy this filter anywhere in the world, you know. And the coal, you just put the coal inside. So you throw away the old coal, or you recycle the old coal, and you put the coal inside here by hand. So it's going to be reusable like lots of times. All right, you have more questions about the filter?
Yeah, a quick question. can you give more detail on how you measure the quality of your filter? Like, is there like specialized equipment, or it's?
So in our university, we have some special equipment to measure fine dust, and I've been asking for that into our university. But then I also built a device which measures the gases and dust by itself, although it's not so precise as the professional one. And I think this uses the typical fine dust sensor, which is the SD something. It's a laser sensor. Yeah, this one. It uses the SD S011, and then it uses lots of MQ sensors in parallel, and also in a redundant way, like the MQ. Yeah, now I don't remember. It's an array of sensors. It's an array of this. Then everything goes into Python, and then Python makes a reading from the serial of the microcontroller, and then this is plotted into a graph. And then, yeah, I don't know if I have the pictures here somewhere. Oh, yeah, I have them on Drive actually. So let me look at it. No, it's not this.
I remember with these sensors, with different gases, you get different results. And what was your result in terms of measuring?
So you have to know that you have to calibrate these sensors beforehand, and there's a complex algorithm that was written in MATLAB for doing that, and then translated to microcontroller code, to Arduino language to make it. And we have pre-calibrated these sensors, and we have let this sensor run for 1 day without gases in our environment, just to create the right offset between the situation with the gases. So here there are some test runs. I did the script in Python. It's a simple script that communicates with the microcontroller. And here there are tests in different materials. So for example, this is our filter results cutting, I think. So here you see there are 2 MQ2 sensors, one on the right, one on the left. And then there's a MQ138, and then a P25 and a P10 sensor. So P25 to P10 are integrated inside the SDS021. Those are PM10 and PM2.5 are the fine dust sensors. So here you can see actually the part per the micrograms per cubic meter, or the part per million ppm, and those are the results. So and although the gases here are staying lower, less than 200 per million, the MQ are for the gases. So the green and the orange are measuring the gases, and then the other one are measuring the 2.5 and 10. But these ones, guys, are way higher than the commercial filter. You see here that they are over 400 for the P25, and almost over 800 for the P10. So those are really, yeah. And we have here a different test. For example, this is the result of the commercial filter, which is made, I think, with the same, yeah, plywood, still the same material. But you can see, guys, those are well below 300 here. But the gases are more. So there are more gases here. Before we were over less than 200, now we are more than 200 parts per million here. So our filter works better for gases, because the commercial filter that we buy now, that by the way costs 500 euros, it uses a very small amount of active carbon. And we have 5 kilos in our filter of active carbon. So this improves the filter and the gas. But the fine dust is still not possible. It's also nice to see that the curves are similar, because in some spots, the laser was cutting for a longer time. You know, the laser jumps after a while and so on. So the curves between the commercial filter and the self-made filter are similar. So you see these 2 spikes are similar in the plot of the flow. Okay, guys, more questions about the filter?
Yeah, thank you. That's super useful, by the way. Like the data like this, you don't get to see very often. So that's very cool.
Thanks. All right, guys, let's have a look now to the CNC quickly, because then I want to show you the machines live. Share screen. So we go to, yeah, let's go to the website first, and then we go to the, yeah. All right, so the next machine is going to be a CNC machine. It's the first time for me to making a CNC machine. So guys, I was also trying to answer some questions. So this is the 3D model of the machine. So my question here was like, okay, let's remove completely the aluminum profile, which might be not the strongest for making a CNC. And let's avoid any kind of connector. Let's avoid T-nuts. Let's avoid brackets. Use the frame itself for joining the different parts. You know. So and for doing that, so that was my main research question about making this machine. Can we make a frame that can join itself directly, that can be bolted directly without using glue, without using press fit and so on? So the answer is yes. The final answer is yes, but it's hard to produce. It's difficult to produce. So what we were doing is basically we were using aluminum plates, and we were tapping on the side of the aluminum plate. This is a 6mm aluminum plate, and it has a 4mm bolt tapping in here. And then we just use this to bolt the whole frame. So this is a preview of the machine. You can see there are these vertical panels with all these holes. So the problem is I cannot put these panels in a vertical way in the CNC and make the CNC make the holes and the tapping. So this has been a poor student from Professor McGill, Kevin, that is also somebody that I really thank for helping me in this machine. All these holes have been tapped by hand. And guys, there are quite a lot of holes for all these things. And also the drilling of this has been done by hand by using laser cutting mask. Because how you put this thing on the CNC, you take again a perfect zero, you know, with this plate that maybe is not so straight and all, to make this holes. So yeah, and here is a picture of the finished machine. So we can go to the CAD, which is actually here. And so here is the CAD of the machine. So the structure of the machine resembles a traditional structure of many other CNC machines. There is nothing spectacular in this. It's worth to mention that we use ball screws in all the axes. So you know, ball screws have no backlash at all. Now you can buy ball screws from China at a very cheap price. So that was also one of the reasons. And then we use again G15 high wheel linear guides to drive the motion. So the machine uses NEMA 24 motors over here with a coupler, and then it basically rotates this ball screw to move this system underneath it that moves then the whole y-axis. I think here we can also have a look to the base first. So this is the base. Yeah, there is another big mistake that made the machine really sturdy, but maybe it's not needed, which is the following. We were using basically this plate on the bottom of the machine, and on top of this plate we were screwing this. This is the plate that we were using here, and on top of it we were screwing this aluminum profile where you can put T-nuts to fix things on the bed of the machine. All right. So this was, I think, a mistake, because I could have used these aluminum profiles directly without this plate underneath it, just by using some rods or profiles underneath it to hold it, without the need to mill and then tap by hand this big aluminum plate under it. So there is a CNC in this Fab Lab that uses this second system that I'm telling you, which is much bigger, much stronger than this. So this was an extra piece that I could have saved. So the base is a very simple system. It has this, again, kind of joints here with a tapping. And then it uses this was an experiment, this big piece of MDF underneath it to increase the weight of the machine and to protect the below system, the motion system, from something that is on the table that could go in there. And so this, I think, is working very well. Although it's not recommended if you use some coolant that can damage the MDF later on. So later on, we will make this out of HDPE in the machine. So the y-axis is, again, this simple linear system. We have milled these gigantic shoulders out of 20 millimeter aluminum profile. So the whole machine is manufactured in my own Fab Lab with my own machines. This is laser cut POM to avoid that the dust will go into the linear guide over here. And then the whole system is still bolted to the frame. So you see here is bolted from the back. So we have made these holes on the back of this shoulder, and then it's bolted also from this side over here. It's different because here we have to have the space for the motor to attach. So, and the motor is attached over here. So the system replicates itself in terms of motion. So there are again 2 linear guides with 4 carriages. We have here the ball screw nut, and then a block that is CNC made by us that stays on the nuts itself. And then we have a Z-axis. And here there is another big mistake that I've been making, which is the following. So I've been using these linear shafts. I think there are 16 millimeter linear shaft with 2 bearings here. And guys, this made this system very complex to realize because these shafts, they need a plate on the top, they need a plate on the bottom, they need these big pieces that we have been manufacturing ourselves to hold the bearings. And to fit the bearings inside, I killed all my bench vices because they were made out of cast iron, and to push the bearing inside, they all failed and broke. So now I have only forged steel bench vices just to do this, just to tell you. And these pieces are complex to manufacture. I was manufacturing them by having a very long end mill, for example, to manufacture these lots, and this was very long. So in the future, I would advise you to also use rails here on this plate to avoid to have this 1, 2, 3, and 4 pieces to produce. So they will be much faster. So then here we have just a holder, and we have our spindle that is removable. There is a sort of clamping system here that you can screw on, and then it will allow you to remove the spindle. So this machine is in the range of 1.5 thousand euros, so 1,500 euros. That will be further reduced, I think, in the future. It was very hard to produce, but then it worked really nicely. And it's really easy with this machine to mill aluminum and to make perfect PCB. So with this machine, you can satisfy the needs of a Fab Lab. And you can also make, I think, you cannot make, of course, big furniture because the cutting area is 600 by 400. But still, you can really use it for almost all the materials that you need. Guys, questions on the model before we go on?
I want to ask, you mentioned the price for the machine. Is that correct? Did you say anything about
the bill of material? Yeah.
And the bill of material, you said 1,200, right? 1,200 euros.
It's no 1,500.
1,500. Okay.
Yeah. So guys, there is a problem, which is, of course, you can buy a CNC 6040 Chinese one for around about 800 euros here in Germany, shipping included. All right. So you ask us why you want to make such a, because this machine, guys, can cut aluminum much faster than the other machine, and it can achieve a precision that the other machine will never be able to reach. So we have more precision and faster speeds, and it's so the first thing I do in a CNC is I take the holder, the spindle, and I try to bend it by hand. All right. If you do this in a CNC 6040, the bending is instantaneous. And here you need to put some force to bend it. So let's have a look to some videos of the machine. If you have questions, guys, please talk over. So on the back, there is the 6040. And here there is this machine. There is another thing, guys, that is very important that we always miss in this kind of small machines, which is the Z-axis. So the Z-axis of the CNC 6040 that is on the back, guys, it's 60 millimeters. Now you ask me what I can do with only 60 millimeters Z-axis. I mean, of course, I can do molding and casting, I can do PCBs and so on. But what if I need to make, like, I engrave a big piece of foam, for example, or I need to have something that is longer? Because in the 60 millimeters, you have to consider also the body length of the tool. And if you put the tool below the holder, the 60, they become maybe 40 or 30 millimeters, and it's super limited. So in our machine, we have 150 Z-axis. So it's more than double the Z-axis of the other machine. So the all electronics of the machine has been separated from the machine frame itself, and it stays in this separated box. So there is again an emergency button with a key, on and off button, and especially guys, also here, we only use now in all the axes these beautiful inductive probes, which they work straight away with aluminum. So there is a converter PCB that we self-made inside to work with this. And the controller is the same of the all three machines. It's still the MKS S-base, which runs on everything, basically. All right, let's have a look to a couple of videos. So with this height, guys, it's super nice to attach a machine vise to it. So you have space to put anything you need on top of it. And you just use T-nuts with this bed and you attach everything. This is a PCB that we have been making with this machine. I'm going to show you. This is a simple, it's a tiny 1614 Hello board. This is the result in milling aluminum. And I've been checking the tolerances, guys, with a micrometer, man, it's almost precise to 0.05 or more than 0.05 precise cutting. So guys, it's really high precision. And we have implemented some additional features. So the first feature is, of course, the homing. So here you're going to see the homing. So this is the homing. It's still done by this inductive probe. And then here is doing the y-axis homing. So guys, it's worth to mention that the precision of the homing is so high that you can switch off the machine, go back to 0. If you remember the machine position, you can resume a job easily after powering off the machine. So this is the homing of the y-axis. And then there is the homing also of the y axis over here. Then there is a sensor for calibrating the tool length. It's almost everywhere. And it's a touching probe, which connects to the microcontroller directly. So it's typically the tool going down and then it goes up after it touches the probe. Yeah, oh, sorry, I think internet is. All right, I think this video doesn't load. Oh yeah, okay, now it loaded. Okay, so wait. So it goes down and then it zeroes the machine automatically. So once it touches, you don't have to push the Z0. It zeroes the machine automatically. So here is the machine milling, sorry for the noise, milling some PCBs over here. You have to consider also the machine is of quite big area for milling these PCBs, so but it keeps a very high precision for it. And here is milling aluminum. Well, I will remove the sound before I kill myself. All right. So here is milling aluminum. It's polishing actually one of these parts. And I think here there is another video about milling aluminum. Yeah, so the first time I milled with this machine, I was having a step down of 1 millimeter with 8 millimeter tool because it was the only one I had at that time. But the machine is able to do 1.5 millimeter step down. So one pass you can go 1.5 millimeters, but it will solicitate quite a lot the machine axis. So I prefer to go fast. I use like 0.5 millimeter step down. So the spindle is a German manufactured one. It costs 200 euros. It's 1 kilowatt spindle. And the drawback of this is that the spindle speed is regulated by hand. So there is a knob on top of the spindle that you need to move to change the speed of the machine. And also, so if you kill the machine, kill the job with the emergency button, the spindle is going to stop. You know, but it's then started still by hand because here there is a big button that you need to push manually to do it. Right? All right, guys. Questions about this machine? Comments? So the answer to the question is yes. We can make a machine like that. And I think I will still use this technique in the future because I saved on brackets. I saved in a lot of T-nuts and nuts. Assembly time was very quick and fast, was self-aligning, everything was very nice. But I will try to find ways to make the tapping automatic. So I'm buying specific tools to make the tapping automatically into the holes, and I would build special fixture systems to hold all these pieces in place while the machine is tapping them automatically. If I don't do so, then it's not anymore convenient to do it by hand because it takes like ages to make it. But also I want to say that almost all of this machine has been fabricated. I mean, all the frame is fabricated. The linear guides, I have also the self-fabricated ones. By the way, just to mention, they are here. They are very precise. This kind of linear guides I've been making in POM, CNC mill aluminum and 4 bearings, but they are not holding the force that I need yet for this. So they move very fast. Yeah, there is a video, but they are still not holding the force that I need. So they need further developments.
Does it has a good speed than current machines available?
You mean this CNC?
Yes, yes. If you compare this CNC with the current CNC machine, then it is a good one in case of speed.
Can you tell me a comparison CNC you want to compare? A model or?
Yeah, some machines are available of China model. So we can say that it
like
is a good one that.
You mean this one, like the China one?
Yes, yes.
Yeah.
Yes, yes.
Okay, so this machine can move that because I have it also in my shop, and it's on the back. This one over here can move maximum 1,000 millimeter per minute. And at this speed, there is a risk that it loses some steps or it has some problems even. So our machine can move safely 4,000 millimeter per minute, and it can mill at that speed. So that is really, it's much faster than this. There is no comparison with the spindle. The Chinese spindle requires a chiller that you need to buy separately to cool down the spindle. Our spindle is air cooled, you know. So there is a hell of a difference. There is a hell of a difference. Of course, also in price. It's like almost double price. Our CNC, yeah. But then there is no comparison in stiffness. If you take this spindle by hand here, you know, you're going to twist instantly the x-axis of this machine, you know, and especially you're going to twist this part on the bottom, which is very thin here, where these rails are attached. In our machine, really, it's hard to twist something. So it's super solid. Look, it's all bolted here, and here the linear guide is here, and these are like 20 millimeter aluminum profile. Then you will ask me, do you need all these profiles? So this thickness, maybe not. Maybe you need a little bit thinner. So for the next iteration.
Okay, thank you for sharing the information.
So guys,
are you considering? Please. Sorry, yeah. Are you considering to add a vacuum bed?
Yeah, that is something that we would like to have in the next version. The vacuum bed will be, yeah. We were considering the plate that I will show you before. Remember this bottom plate as the vacuum bed because it has all these holes, and yeah, that's for sure something that can be considered. Yeah. So now the machine, it's completely enclosed. Also, they build a housing around it, and the next modification will be the coolant system to cut aluminum. So we are going to put a recycling system to recycle the fluid, the coolant, and then we are going to spray the coolant onto the head. More questions, guys?
Quick question. How much do you think you can scale this? Is it 60/40, or do you think you can make it bigger if you push some?
Oh man, I think so. You can scale these, I think, so much because, for example, the bed that is used right now, that is 16 millimeter height aluminum, it's in use in a CNC that is here, which is 1 by 2 meters. Only the bed. So, and this bed is stronger than that machine because it has this plate. You would, of course, change the motors. You would, of course, have a separated motion actuator, so you don't want to put the shaft of the motor directly the ball screw with a coupler, but you have another belt and pulley. And then the rest, you increase the size of the shoulders, for example, the thickness of the shoulders, and then you can scale it up as much as you want, I think, like full-size shotbot. But then I warn you, if you do a full-size shotbot of this kind of machine, you know, you're going to need like 1 ton of aluminum. And aluminum, although here in Germany is very cheap, would be expensive in that scale. So in that scale might be, you know, that the shotbot doesn't have a bed. You can put a piece of wood in 2 beams, you know, and you have it. The frame of a shotbot is made just by profiles, you know, and in that scale, this will result in a much cheaper machine. The shotbot is empty, you know, it's made by these big aluminum profiles here, you know, and yeah, so the answer is yes, but it could be very expensive to make it.
Very cool.
Guys, more questions? So we go to. So guys, these machines are the CNC and the 3D printer are already published as open source. You go and download them yourself. The documentation is really poor, but it's in here. All right, there is a GitHub repository. You have the firmware. Okay, I still have to upload the 3D model for this, but I will do it really soon. So you can download it. I'm going to post this in the chat. There are some questions, I think. All right, this one is, in a second, everyone. This is one. And the other one is also already published online. I think 3D model is also already here. For this one, guys, you go and download anything. The laser cutter, as we discussed, we have some issues with safety. It's still not published. All right. So I did put the link in the chat. All right, guys. I think you're ready for some action. Unless you have some more questions that requires me to show something on the screen. All right. Oh, yeah.
Not really a question, but a comment. Gianluca was asking, can you scale up the Sensei to a bigger machine? The answer is yes, and nothing stopping you using steel parts instead of aluminum ones that you get water cut somewhere or however. So that would be possible. The other thing is to scale down the MidFDM. So you could make that quite a bit smaller using the same basic constructions. The limiting size is the head, of course. But if you scale down the MidFDM, you end up with essentially a self-made, any size you want, very similar to any of the commercial printers. And I think the other answer, based on our experience, I mean, Daniela is being very modest here, but this aluminum machine, the TseNC, is actually doing stuff that those 6040 can't do. It's cutting aluminum at speeds that you just simply can't do with those machines, and the repetition is fabulous. So it is a lovely machine, and in comparison, I've been searching for similar machines of the same kind of quality. And in Germany, while he's moving to show us the machines, in Germany, the similar kind of quality of machine to buy from a local manufacturer, you're looking at 2x, if not 3 times the price of the bill of materials. So it's an intermediate machine. It's not one of those cheap Chinese machines. It's definitely not that. But it's getting toward some of the professional machines. And I've seen a couple of professional machines that aren't as stiff as the little CNC for that size. So I'm not trying to sell it, but I love it.
So guys, another point about all of this is that to scale up these machines and to make them, you know, like also better and cheaper and so on. Of course, if you go to the industry, steel is the way to go. You know, you find companies that will laser cut or water jet steel for you, will bend it in any shape you want, will tap it, will make it square since the start and so on, and then you can make it. But the point of these machines is that there are still something that you can do in the Fab Lab. You can still mill all this aluminum in the Fab Lab. And that's one of the big struggling that I also have personally. Do I want to go to the industry and then sell machines, or do I want to stay? And I'm struggling every time I add a component because I'm forced to use this Fab Lab friendly material, you know, and that's not so easy. All right, guys, I'm going to start showing you the machine live. I'm still connected with you, and you can anytime ask us for questions and stop me. Okay, so please speak over because I'm not going to read the chat. So please pin the other camera from me, I think you find it. There is a printer printing right now at this moment. I hope you find it. Please let me know if you find it. Do you have the other pin? All right. Chris and Haru and Gianluca, you have the pin?
I think I'm not familiar with the concept of pins.
Okay, just over the mouse to go to the gallery view. And then hover with the mouse to my Daniele and Garcia screen.
Got it. Got it.
And then there is 3 dots and then pin.
Yeah, found
Gianluca.
it.
Yeah, I think you can double click on the image as well, and that should pin it.
All right, so I think everybody's set. So the first machine I'm going to show you is MidFDM. I'm going to do it, William, I think it's fine. So it's printing right now. You can see the system in motion. Oh, thanks, William. So I can show you a bit better. So here is the system in motion. So the motion is still rather smooth. I think you can almost see no vibrations. I'm going to show you from the side of the machine as well. I hope this follows me. So this is the furthest point you see of the motion of the machine, and you see that there is almost no shaking at this time of the machine. So the machine takes the whole table at this moment, and it's yeah, here are the doors that can be closed, and yeah. Can you hear me, guys?
Yep.
Yeah. Okay. Right. All right. Here there are some attempts that have been printing. We had a huge problem with this rocket because at a certain height the printer would like have a shift or stop printing. So here you can see the shift, and then we were able to print all of this correctly. Here there was a shift also, and then here there is the full rocket printer. Basically, the controller was sending pulse rate to the driver faster than the driver could actually receive it, and the driver was keeping some movements after a while. That was one of the problems. You can also see this vase that we've been building. This big vase, you can see at the top is a little bit more shaky than in the bottom. In the bottom is a little bit more uniform, but in the top is more shaky because, of course, the more vibrations are in the top. So
Probably have to speak a little louder.
all right. Guys, do you have questions, comments, things you want to know? All right, so we will leave the machine. And we will go to the laser cutter now. So by the way, this is the Fab Lab from William. All right, so the laser cutter is here. So guys, the laser cutter is a very simple setup, and it can stay in a table. Also the filter is very small, standing on the side. Here we have some real-time, so some real examples that have been. This is an engraved picture, for example, and laser cut 6mm plywood. This is an example of fluid bending that we've been making with this machine. Here we have another example of the precision of the machine. Here we have 10mm acrylic cut with this machine. Here we have my business card, which lines are 0.05mm width, engraved with the machine. And some other pieces, drones, and some other things that have been done with the machine. So here is the machine. There is a light inside, and there's a job that has been paused for you guys for seeing it. So I'm going to show you. I'm going to switch on the filter. And then I'm going to switch on the pump for the air assist. And then here is the G code. It is being paused, so I will just send it now. And here is machine cutting. So we are now cutting 6mm plywood. And so every time you open the lid, this will automatically stop. Maybe we'll show this also on screen. So now, for example, the machine is not cutting anything. And as soon as you close it, it's going to cut the parts. So this is 6mm plywood, and we are cutting it at a speed of 500mm per minute. Okay, just to give you a reference. So, and maybe the settings are too conservative because you can see that the pieces are falling down, but probably, yeah, we could have launched it a little bit faster. So, and just for you to look the machine, here is the emergency button on the key. So if you push it, it's basically then you can take the key with you and then you can lock the machine. The overall machine, as you can see, is rather compact. So this is something around 38 centimeter in height and 80 centimeter in width. And the system, it's staying in this table. So you can drive the machine with a computer. So the machine runs on a GRBL, of course, and it can pause, resume jobs. It has many functions, of course. And here you can see we use universal G-code sender. There are many G-code senders that you can use. And then you can see in real time the machine moving. So to slice the, so to prepare the G-code, we use a software which is called VisiCut. And VisiCut is just open in here. And it's very easy to use an open source software, guys, for generating the G-code. It can order the layers in colors, by layer type, by ID, if it's a curve, if it's a line. You can launch engraving with different strategies like Yarvis, Spooky. It's really powerful software, open source software that you can use. You have material library in this software. You can save the settings for each thickness of each material. You change the resolution also of your machine. It's really powerful software. I really highly recommend it. It was done in Hagen University here in Germany. So while we are talking, the machine is still cutting. I will show to you a cut of 10mm acrylic. But I would like to wait that this is finished, and I can tell you it's almost finished. Do you guys have questions in the meantime about the machine or anything? So it's also quite silent if you can hear me, because now there is filter on, pump on, everything it's on. But yeah, you can also see the smoke is going to be taken like almost instantly from the filter. So it's quite efficient in terms of exhausting the dust and the smoke. Yeah, and now it's cutting the outside, which is actually the last step to do. So the machine, guys, another thing to mention, doesn't have a Z-axis. And this is to save on cost. So to change the focus, what you do is you need to change the height of the head. And you can do that by using a screw and then a stopper washer. So then there is a stopper that you rotate and stops the height of the head. So for the screws, and with this lens that we have, we often don't even change the focus. So for cutting, the focus is fine between a certain, for example, between 6 and 8 and 5, it's still more or less okay. You will lose some performance, but still more or less okay. But it's highly advised to change the focus when you do the engraving, because then in the engraving, the spot size will make the difference. So if the engraving is out of focus, the spot size is big, and then you're going to get some problems in quality. So the spot size, the best one is 0.1mm, which is something that was achieved in this picture over here. Yeah. All right, so I think the machine is almost finished. I will do this, and then we go to the Cnc. Okay, let's wait a few seconds that the smoke is out. I think it's finished, so we take the piece. Yeah. Yeah, with one hand is not the best. Here is our piece, fresh and made. All right, I'm going to So the bed, guys, is also something that this bed has more than 1 year, and you can clean it easily. So you just pass here some paper towel with water, and then you can clear all the bed. This bed was already cleaned after 1 year of use. So I will now cut this 10 millimeter acrylic machine. So I will just put it in here. So the holding of the machine, you can take it by hand. So just move the head wherever you want, for example, and you have it here. Or you move the piece wherever you want. Then we close the machine. And we go here and we open the G code, which is this one. Yeah, which is a very simple circle. So we reset the 0 for the positioning, and then we're ready to cut. 3, 2, 1, play. And guys, now we are cutting 10 millimeter acrylic. Okay, so there are no flames, guys. The air assist works beautifully in this machine, guys, that you don't have any flame when you cut, and it creates really a clean cut. And now it's almost done. So it's a circle of 1 centimeter right now. All right, so let's wait 2 seconds that the smoke is going out, and then here we have our 10 millimeter piece of acrylic being cut. So it's not so easy to handle with one hand, but right. So, and you can also see, guys, that it's almost perfectly straight, and it's 10 millimeter, guys. So in this, I'm very happy with this machine. That's yeah, it can do really many things. So let's switch it off with the emergency button. Switch off the filter and the pump, and then we go to TseNC. So here it is. All right. So here is our
Time is
machine.
getting short.
Awesome. Here is our machine. It's completely enclosed at this time. And our colleague Aaron that works here in this Fab Lab, he built this beautiful housing at aluminum profiles. So the machine stays inside the housing. You can see it over here. It's a little bit dirty right now because we are actually cutting aluminum. We are stopping a job for you guys to see it at this time. So we will show you a couple of pieces that we made. This is actually the PCB that was made with this machine. And this is the beautiful piece of aluminum. And one thing that you realize, guys, is that the finish is almost mirror here. There is almost no shaking in the motion. So it's super, super smooth. When you have cheap machines, the first thing you see, it's a lot of shaking here, vibrations, or roughness of the surface. This is like a super smooth surface here. All right, so this was one piece. So now the machine still runs with GRBL, and it's ready to start. So we have to open the lid. Then we have to start the spindle manually because, again, it's started by hand. We started. Then we close the machine, and we resume our job. So we push play. All right, guys. And here you have our machine. Yeah, I hope my camera is good enough to see some milling. So now the step down is really conservative. We are eating 0.5 millimeter step down. It's super, super conservative. And then at the end of this, there will be a finishing pass that will smooth the whole surface on the outside. There's going to be a finishing contour strategy. Yeah. So every once in a while, we also put some lubricant into the machine to avoid that the aluminum sticks to the tool. Yeah. So to detach the spindle is a matter of a second with that 2 screws that you see on the right side. In case this spindle, for example, it's worn out, or you want to change it with something that has more performance. So you see the speed of the jumps. The jumps are done at 4,000 millimeters per minute. But aluminum milling is really safe now because I didn't want to risk anything also with in camera lens with you at this time. So. All right, I think we are 7 minutes from the end of the conference. So the workshop, no, actually we are already over. So yeah. 10 minutes. So I will show you a little bit maybe the machine from the side as well. All right. Before I leave the machine, guys, do you have questions or comments?
Pause it.
Yeah, I will pause it so there is less noise. All right, I will stop this window. All right. All right, guys, thank you, William. Do you have more questions and comments?
Thanks. This was really a good insight. I would like to maybe you have a little bit more details about the CE certification. So like first details, first limitations that you're facing.
All right, so we are trying to make the CE certification for the laser cutter, which is the most critical machine in terms of safety that needs to be certified. And it's our more, let's say, mature product or development. And the first step of getting the CE certification is to buy all the components that are already CE certified. And this is sometimes already an issue because, for example, okay, the motors and the things that are coming from Germany are easy to get certified. But the laser tube, it comes from China. And to have a laser tube that is certified, actually we are buying it, but it costs 3 times more than the cheap, not certified one. Okay, this is the first thing. The second thing is that everything must be working together as still being certified. In laser, for example, part of the certification is also the assessment of the laser safety. And the lasers is divided in 4 classes, with the class 4 that is the most dangerous. So, so for the CE certification, basically we need to declare all the specification of the machine and document what could be all the risks involved using it and what are all the measures involved in minimizing these risks. So which kind of sensors we use, how do we close the machine, could it take a fire, and so on. Some things are easy to do ourselves because, okay, I just write the specification of the sensor that I use. It can resist to this temperature, the machine will work with this temperature, I'm fine. For other things like electromagnetic interference of the 18 kilovolts, I need somebody that measures the EMG of the machine. Then I need somebody that classifies the machine as laser class 1. So it certifies that the speed of the sensor is fast enough to make sure that the machine doesn't shoot and so on. So one of my team members that was in the previous call, Mark, he is looking into that because I can do it as a also hardware developer. So we hope that we can get a certification in some time, by the end of the year or beginning next year. All right, guys, further questions, comments on the machines? So we are getting there, huh? These machines have been made by us. They are not bought, but we can do almost what we need for a real Fab Lab. You know, it's not a joke. Yeah.
And then for the CNC spindle, so how much it would increase the cost if you would buy a spindle that you could control the speed through G-code?
So controlling the speed through G-code is not the key factor for the cost, because you can get the cheap Chinese spindle for around 80 euros. And it's also 1.5 kilowatt, you can control it by G-code. If you want to have a German one, with the controlling of the, then this price increases like a lot. Yeah. So
you could also hack into the controls of this. It depends on how far you want to go with your hacking, but yeah.
Well, this is controlled by just a knob. So you just open the spindle, hack the potentiometer. You have done it. Let's say, although it's not
does
so.
Does it have you know like just the 1, 2, 3 as a speeds, or it has actual RPMs?
It has a knob that you can go in between.
Yeah.
And I don't know if I can show it to you.
It's 1, 2, 3.
Yeah, and let's remove the camera is still on, I think.
Yeah.
So William is showing you, and there is a knob basically that is not any steps, so you can continuously move. So between 2 and 3, there is a lot of positions, you know, and then you have the speeds are on the side. So William, maybe we can show the speeds.
Oh, right, the little table.
Yeah, there is a label on the other side, and there is a speed. So this spindle, guys, I don't like the sound. I hate it.
I got it.
Yeah, you got it. You got now the table with the speeds. Yeah, they got it. Thank you. But till now, has been proven to be very good. So I hate the sound that this thing does because it seems that it should explode like after 2 minutes. But till now, it's all worth of it. It's air cooled and it mills aluminum like butter. So.
Now, may I mention something? Marvell is one of the premium manufacturer in industrial machines. So the motor, the milling thing is one of the best on the market in this class, to be honest. On my mill machine, I have got like an from Cress, similar to this one, but the next one, if you know, if this one is done with mine, I'm gonna get a Marvell. Because a friend of mine has a bigger milling machine and he's even milling steel on that. Yeah, it's amazing, but it's quite loud. That's really.
All right, then the spindle, this one costs 200 euros. The Chinese one you can get for 80 euros. But you need a water cooling system, chiller and so on. So it's really worth it to have it like this way. But of course, you need to increase the controlling of the RPMs.
Another question related to CNC. I really appreciate the box that you built around it. Have you measured how much noise it is able to reduce?
No, not yet. We will. We have a sound meter. With the box we just finished yesterday. So as soon as what we want to do is to look at it. At the moment, the glass is still vibrating. There's no inserts to hold the acrylic against the profile. So we need to do that first. And once we've actually insulated the acrylic from the aluminum frame and put some inserts in, then we'll do those measurements. Because I think, yeah, it's going to make, I'm guessing, but it's going to be a 10 dB difference. I don't think it's going to be much more than that, but it certainly does make a huge difference. Also, and you can't see it from the picture looking at, but there's a great big hole. I mean, we've actually got a great big hole underneath here because we haven't finished the lubricant and the cooling system for the bottom. So at the moment, it's just open here. So there's a number of things we still need to do to the housing to encase it. And every one of those that we do will drop it down by a few more dB. But my guess is we've probably got a good 10 dB just through the housing at the moment. Yeah. But that's a guess. I'll give Daniele the details when we get that further.
So a question: if you're going to include the casing into the kit once you're going to do the measurements, and are you going to open source it as an accessory?
Oh yeah. The casing is really straightforward. We'll draw it up and include it. Yeah, no problem. Yeah. Sure.
Yeah.
Is it a torpedo on the background that you have there? There's like some sort of a rocket in the background on the ceiling. So what is that?
Yeah, those are the powered submarines in the lab. That's a whole other talk.
Yeah. One thing about the housing is, I mean, this housing, you know, as these profiles, and maybe we can build another CNC with these 3060 profiles. It can be made also with 2020, probably next time.
Yep.
A little bit cheaper than this one. But this one is really rock solid. I mean, it's made to last, really.
Yeah, now we can stack them. We can do double decker CNC.
No,
Yeah, I'm asking you because I'm kind of in the process of I'm helping to plan a lab, and if you so there's some DB requirements for certain type of spaces, and it just would be, so let's say if a lab would be built in 5 years from now on, and this machine would be open source, and let's say CE are certified, then it would be just very good to know, what is the maximum noise level that it's making.
other things.
We'll make the measurements and let you know.
Yeah, Chris, we are in touch on Facebook. Yeah. Another problem that this machine has is that this kind of protection that I laser cut here, they're not enough to protect the guides from aluminum. So now they have aluminum on them. Yeah, so we need to improve this system, because otherwise the guides will
once you have the flow. So we're gonna make a recycling. If you turn the thing around, there's a big mill behind us here. So we're gonna use the same system as that has for its cooling system. So the flow comes right over the head, and with the liquid cooling, then the swarf is no longer gonna get under the rails.
All right, guys. I think it was an amazing session. I don't know if you have more questions. I'm available to stay longer. Otherwise, I need to crimp the cables of our next kit for the laser cutter. Yeah, I need to deliver 2 kits today, this evening. So just to let you know.
Thank you very much. There was a great presentation.
Well done, Daniel.
Thanks. I hope you see the video. Konstantin, please come back.
I'm planning to come within the next month, Bob.
At least visit. And also you, Bob, Chris. Bye. You're welcome, everybody. Hey, bye. Bye, guys.
Bye.
Bye. Thank you.